Namaste. Myself, Dr. Mrs. Preeti Sunil Joshi, working as Assistant Professor in Walchand Institute of Technology, Solapur. In this session of Crysallography, students, we are going to learn about calculations of different parameters of a cubic lattice. The learning outcomes are, by the end of this session, students will be able to define and calculate various parameters related with the cubic lattice. The contents include volume, then number of atoms per unit cell and coordination number. Dear students, in the previous sessions we have learnt about crystal systems and Bravais lattices. So to proceed further, let us recall the terms what is meant by unit cell and Bravais lattices. I request you to please pause the video, think for a while and try to answer. Yes students, you are correct. Bravais lattices are the 14 different ways of arranging identical points in three-dimensional space, which satisfies the condition of periodicity. And unit cell is the smallest volume which carries the full description of the entire lattice. Well, a unit cell is characterized by a set of characteristics, that is volume, number of atoms per unit cell, then coordination number, atomic radius, atomic packing factor and density. These parameters can be computed with relative ease of cubic unit cells. So there are three Bravais lattices for cubic structure. They are simple cubic, body centered cubic and face centered cubic unit cells. So in this session we are going to study in detail the parameters, that is volume, number of atoms per unit cell and coordination number. Now let us see the first one, volume. A unit cell is said to be primitive when the cell has lattice points only at its corners. The primitive cubic unit cell is also called a simple cubic unit cell. In case of cubic cell, all the edges of the cube are of equal length A, therefore the volume for SE it is given by A cube. Then for BCC, it is having the lattice point within the cell in addition to 8 corner lattice points as shown in the figure here. In case of cubic cell, all the edges of the cube are of equal length A, hence the volume for BCC is also given by A cube. Then the face centered cubic cell, it is a non-primitive cell having 6 lattice points at the centers of its 6 faces and 8 corners of the cube as shown in the figure. So here in case of cubic cell, all the edges of the cube are of equal length A, therefore the volume is given by A cube. Now the next parameter is effective number of atoms per unit cell. Let's see for simple cubic structure. A unit cell is a part of an infinite scheme and it is not an isolated entity. Therefore, several adjacent cells share each lattice point. So as a result, the basis attached to a lattice site contributes only a fraction of its mass and volume to one unit cell. The effective number of atoms per unit cell is given by Z is equal to ZB plus ZF by 2 plus ZC by 8, where ZB is the number of body centered atoms, ZF is the number of face centered atoms and ZC gives the number of corner atoms. In the three-dimensional array, each corner atom is linked to 8 surrounding cells as shown in the figure. Hence, in effect, the atom contributes 1/8 of its content to a unit cell. Simple cube, being a primitive cell, does not contain lattice points within the body, volume or in the center of faces. Therefore, the total contribution to the cell, it comes from the corner atoms of the unit cell and is given by Z is equal to 0 plus 0 plus 8 by 8. Therefore, it is equal to 1 atom per unit cell. Now for body centered cubic cell, it has 8 lattice point at the 8 corners of the cube and 1 lattice point at the center within the cell. Therefore, there are no points in the face. An atom at the lattice point within the cell belongs completely to the cell, and atoms at the corners of the cell contributes 1/8 each as shown in the figure here. The effective number of atoms per BCC cell is then 1 plus 0 plus 1, which is equal to 2 atoms per unit cell. Now for FCC, in a 3-dimensional array, a unit cell is surrounded by other unit cells, while each corner of the cell is shared by 8 adjacent cells, and each face is shared by 2 adjacent cells as shown in the figure here. Therefore, each face centered atom contributes half of its mass and volume of one cell, while each corner atom contributes 1/8. Thus, the number of atoms effectively contributing to the FCC cell is 4 atoms per unit cell. Now let us see what is meant by coordination number. The coordination number of an atom in a crystal is the number of nearest neighbor atoms. It actually signifies the tightness of packing of atoms in the crystal. So we can define coordination number is the number of nearest neighbors of a point in space lattice in a unit cell. Now let us see the coordination number for simple cubic structure. Around an atom in a simple cubic cell, there would be 6 equally spaced nearest neighbors, each at a distance of a from that atom. So 4 atoms lie in the plane of the atom, while one is above it and one is below it. Therefore, the coordination number is 6 for simple cubic structure. In the BCC cell, atoms occupying the corner lattice points do not touch each other. However, each corner atom is in contact with the atom at the body center. As there are 8 unit cells around each corner of the cell, the atom located at a corner would be simultaneously touched by the 8 body centered atoms of the 8 surrounding cells. Hence, the coordination number is 8. In a FCC cell, each corner atom is in contact with the face centered atom. It would therefore be in contact with 4 atoms in its own plane, 4 in a plane above it, and 4 in a plane below it. Hence, the coordination number is 12. Students, now pause the video and try to solve this numerical. Copper has an FCC structure with lattice constant 3.61 angstrom in it. Calculate its radius. Students, please check your answer. We have to find here the radius of FCC lattice. So, formula is √2a by 4 and the correct answer is 1.278 angstrom in it. Now again try this numerical. Check for your answer. Correct answer is 4.93 angstrom in it. So students, please go through different reference books and practice more numericals. See you in the next session. Thank you.